Everyone, this is Mrs. O'Reilly here to talk to you about radiation and climate. This is Unit 4B in your book. Our objectives or our goals for this chapter is to look at the major types of electromagnetic radiation and which ones are part of solar radiation. We're going to look at the relationship between energy, frequency, and wavelength. We're also going to look at how that solar radiation interacts with the Earth's atmosphere. We're going to compare thermal energy with heat capacity and reflectivity. We're going to look at the greenhouse effect, and we're going to look at the carbon cycle and how those are impacted by humans. So first, we have the electromagnetic spectrum and solar radiation. So the electromagnetic radiation is just a broad range of energetic emissions. So here's a visual to help you kind of understand it. On this end, we have gamma rays. They have really short wavelengths. So the peaks come more often, they go up and down more times, which means there's a higher frequency. Every time it goes up and down represents the frequency. So the more times it goes up and down, the more frequent it is and the higher frequency. This also takes more energy. To have a higher frequency, it takes a lot of energy. So on this end here, you have short wavelengths, but high energy, high frequency. And that's like a gamma ray. X-rays are a little longer wavelength, then you have UV light, visible light, infrared, microwaves, and radio waves finally is your longest wavelength. Those long wavelengths have a very low frequency. They don't go up and down as frequent, and they have lower energy. So because of this, we're going to bring back those proportionality words. Wavelength and frequency are inversely proportional. Frequency and energy are directly proportional. And wavelength and energy are also inversely proportional. So how does this relate to what we're talking about? Well, we're talking about solar radiation. The kind of solar radiation that we experience here on Earth includes 3 of those types of radiation from the electromagnetic radiation spectrum: infrared, visible, and ultraviolet, which we call UV. Infrared is like your heat radiation. It's absorbed by the carbon dioxide and water vapor that's in the atmosphere, and it doesn't all reach the Earth. And that's this region here in the graph. So you have infrared is from this area over here, and this is the length of the wavelength. So notice where it was a longer wavelength, and this region here is the infrared. Slightly shorter wavelengths is visible. Visible is scattered by water, air, and dust, and that's what allows us to see these really colorful skies. Imagine a prism. You know, when you see little rainbows dancing on the wall, it's reflecting off of something with a lot of edges, and that's called a prism. Those are the different colors, different wavelengths of visible light that we see. So when you see a blue sky versus the sunset or the sunrise, it's orange and pinks and yellows. That's all because of the way the light is bent and the different lengths of the different wavelengths of light energy that's being emitted at that time. That's your visible region. And then you have UV. This is the part that we worry about a lot. Includes UVA, UVB, and UVC. It's the highest energy, more frequent, more peaks. We can actually use this to sterilize. This is the highest energy, for solar radiation, but not overall. We can use it to sterilize materials. It can kill bacteria, and it can even destroy some viruses. So looking at what percentage of solar radiation comes from each, 45% is from the IR, or the infrared region. 46% is from the visible region. And 9% of our solar radiation is in the UV or the ultraviolet region. Earth has an energy budget. We have this solar radiation that's coming in, but it doesn't all actually reach the Earth. So only about 30% never actually reaches the Earth at all. It's reflected back by the clouds and the atmospheric particles. You can see this here. This is infrared radiation that's emitted into space. It's reflected back. Then there's another 70%. It's made up of 2/3, which is about 50%, close to it, absorbed, warming the atmosphere, oceans, and continents. So that's what's actually absorbed, the energy absorbed by surface and atmosphere. That's that 2/3, so about half of it. And about 1/3 powers the water cycle. So what that means is it heats up water and evaporates the water, turns it into clouds, water vapor, which turns into clouds. When those clouds get heavy and they reach cooler temperatures, falls down, it condenses and falls back down as rain. So all of these different areas here are showing what's happening in that case. Overall, the solar radiation just comes right through here from the sun. And then if you notice, some of the wavelength is longer and some of it is shorter, and that's to demonstrate what kind of wave it is. So what does this have to do with our climate? Well, to help us with that, we have to talk about greenhouse gases. Greenhouse gases are any atmospheric gas that absorbs infrared radiation, or that heat radiation. The greenhouse effect is when those gases that are considered greenhouse gases actually trap the infrared radiation, or they return the infrared radiation, like carbon dioxide, water, and other atmospheric molecules. So without this greenhouse effect helping keep our atmosphere warm, trapping in that heat, we didn't have that blanket over the Earth of greenhouse gases. The scientists estimate that our planet wouldn't be any warmer than negative 18 degrees Celsius. To give you an idea, 0 degrees Celsius is freezing. So all forms of water on Earth would be frozen at this temperature. This would be the average temperature. So for the most of the Earth, this would be the case. So this is a diagram from your book. The sunlight shines down on Earth as solar radiation. Some of it is reflected radiation right by the atmosphere. It doesn't actually reach the Earth's surface. Some of the infraradiation is just kind of goes back and forth within the greenhouse part of it, that greenhouse cover. And some of it's just absorbed. Also, once the Earth heats up, it releases heat, kind of like if you put your hand on the warm pavement, you can feel the heat coming off the pavement too. Now that was heated by the sun originally, but then that heat is also being released by the surface of that pavement, and you can feel that heat coming off. So that's happening on the Earth too. That infrared radiation will also be emitted back. And that's coming from the Earth. So how is this related? Why does this matter? Well, it kind of flows like this. Solar radiation, the heat from the sun, shines down on the Earth, and it heats the Earth. It heats the land, it heats the water. Then that surface, the Earth's surface, in turn, emits some heat energy or infrared radiation and warms the air above it. So now you have all this air that's right near the Earth's surface that's warm. That warmer air expands, the density decreases, and when things are less dense, it rises. You know, heat rises. When the heat rises, cooler air from out in the outer parts of the atmosphere will come down towards the Earth and replace it. What this does is it creates air currents that drive the world's weather. Now, you might have heard that our weather here in the Northeast comes off of the jet stream. So I included that weather diagram. Now, this is not the current weather. This is just a picture of the jet stream. This is a pattern by mid-August. The jet comes from over here. This purple flow right there of the weather, that air current that our weather travels on is called the jet stream. This is due to that solar radiation and all that different reflection and that changes in the air currents. So what is this, how can we take this further? Well, reflectivity and specific heat help us understand what surfaces kind of allow us to kind of be a part of this. Reflectivity describes how much light is reflected. So we know if we wear dark clothes, it's going to absorb heat. Forests are darker. They absorb the heat from the sun. But light-colored surfaces, if you say wear light colors in the summer because it reflects the heat off of your clothes. It doesn't absorb it and keep you, otherwise you get so hot. Well, snow is light-colored and it reflects a lot of the heat back. So that's related to land surfaces. Specific heat is kind of how much is absorbed. And it's the specific heat capacity is the formal term, and it's the amount of heat that's needed to raise the temperature of a sample. And there's certain numbers attached. So it's the specific value of heat energy that's required to heat 1 gram of your sample 1 degree Celsius. And if it has a high specific heat, it means it takes a lot of energy to heat it up. Water has a high specific heat. You see it at the bottom of this graph. Gold has a lower specific heat, so it's going to heat up a lot quicker. So when you're adding 1 calorie of heat, water doesn't change temperature that much, but all of these other ones increased a lot more. So they have a lower specific heat. It doesn't take as much energy to heat them up. So then we have the carbon cycle. The global carbon cycle is the natural movement of carbon atoms in the Earth's systems. So we're looking at this diagram over here, and you have carbon dioxide in the atmosphere, so that contains carbon atoms. That in turn enters into the photosynthesis process. So plants take in carbon dioxide and turn it into nutrients and oxygen. This carbon dioxide also gets dissolved in water and can end up in limestone and back into the Earth. Those plants that take in the carbon atoms and turn it into glucose. That glucose is then in plants, right? So that plant can go to animals, and the animals eat those plants. Now that carbon atoms are in the plants and digested, and it goes into the carbon dioxide that we breathe out in terms of respiration, ends up back in the atmosphere. Plants also can respirate a little bit and can in turn release carbon dioxide back into the atmosphere. Plants can also decay. When they decay, they become fossil fuels. They're burned through combustion. They become carbon dioxide in the atmosphere. Volcanoes also release carbon dioxide into the atmosphere. And remember, we have this combustion reaction here. So anytime you burn a fossil fuel, burns in the place of oxygen, produces carbon dioxide. Water, an energy source, which is what we capitalize on. So how did humans impact this natural cycle? Well, since the 1800s, the carbon dioxide levels in the atmosphere have increased 30%. So this can happen by clearing forests, burning scraps and timber, or burning fossil fuels. So how does this impact global change? Well, there's a lot of greenhouse gases. So if you see this list here, carbon dioxide is a greenhouse gas, methane, nitrous oxides, water vapor is actually a greenhouse gas. It will still trap and absorb, because it says it has such a high specific heat, it will absorb that heat in its molecules. Ozone, trichlorofluoromethane, and difluoromethane. All of those are greenhouse gases that get emitted into the atmosphere. When we increase carbon dioxide or any greenhouse gas, it's going to increase temperature. When we increase temperature, more water evaporates. When we do that, there's more greenhouse gases in the atmosphere because water is a greenhouse gas. With this, another factor is that when there's more water vapor in the air, it's predicted that that would also mean that there's more cloud cover, and that might counteract some of that predicted increase in overall temperature. So the Earth might not warm as much. So these temperature increases over the years is in this graph below. So it's in the 1800s, 1880, you can see this steady increase. Now, the annual means, the annual average is the black line. Notice there's lots of valleys and peaks. It goes up and down a lot. The red line shows a 5-year running mean. So it's like the current year and the 4 years before it to make a 5-year mean. There's more consistency there, but there's still a very significant upward trend on this graph. This will impact our Earth by creating a rise in ocean levels, coastal flooding. In North America, you could see regional climate changes, which would change the regional crop production. So what can we do about this? Let's review. So radiation is electromagnetic radiation from solar radiation. Includes 3 types of radiation: infrared, visible, and UV, or ultraviolet. Energy and frequency are directly proportional, while wavelength is inversely proportional to frequency. How is this impacting climate? Well, Earth's atmosphere reflects and absorbs solar radiation. Reflectivity implies that light surfaces will reflect energy and dark surfaces absorb that heat energy. Heat capacity is the amount of energy it takes to heat something up. So a high heat capacity like water takes a lot of energy to heat water up. Greenhouse gases are those that trap heat into the Earth's atmosphere. When we increase greenhouse gases, there's a predicted warmer global climate. And the human factors can affect both the carbon cycle by increasing our carbon dioxide emissions and therefore our global climate. Thank you for watching. As always, if you have any questions, please send them my way. Have a great week, everyone.